Good afternoon. Welcome to the Sequitur Labs webinar on behalf of the GlobalPlatform TEE Hackathon event, talking about OpT, running OpT on the Raspberry Pi 3. My name is Abhijit Rane. I'm the VP of Marketing at Sequitur Labs, and I'll be talking through a couple of slides on the intro and then turning it over to Phillip Atfield, who's our CEO and our chief hard problem solver in the office. So let's get right to it. Just a quick introduction about Sequitur Labs. We are a company that is focused on developing solutions to secure connected products and systems. We have substantial expertise being involved with the trusted execution environments over the last couple of years, actually a little more than that, working with trust zone and embedded systems, both on the mobile side as well as on the non-mobile side. We are currently focused on applying this technology and evangelizing trust zone and TEE to support IoT use cases and other embedded use cases, specifically non-mobile phone use cases. In terms of our team, we have deep expertise in both hardware design as well as software design and architecture. All the way, it's a full stack capability, really, going all the way from the hardware level through the OS, virtualization, all the way to the application layer. Specifically around security, networking, telecommunications, systems management, policy platforms, and the associated tools such as compilers, debuggers, and other kinds of tools. Our partners are companies like ARM, Trustonic, NXP, Microchip, with Atmel, really, and since the acquisition with Microchip. A little bit about Phillip Atfield. Phillip is a contributor to the Linaro security working group and was instrumental in actually porting the OpT trusted execution environment to the Pi 3 platform. And he's going to talk a little bit about the anatomy of the port and what was involved as part of this presentation. Although the presentation is going to largely focus on making sure that the developers who are participating in the hackathon are able to set up their environment, as needed. Phillip has been a past presenter at GlobalPlatform seminar events and brings over 20 years experience in a variety of technology fields, ranging from networking to security, large-scale systems modeling, synthesis, and verification. In his prior to starting Sequitur, he's done stints at a number of companies, including Nortel, and was also part of the Phantom Works division at the Boeing company, where he was a distinguished engineer. So I'm going to turn it over to Phillip Atfield now, who will walk through what you folks are going to need and how to set up the environment and for this hackathon. Phillip?
Okay, good morning, everybody. Good afternoon, wherever you are. So we're going to walk through a set of setup slides as well as some information on the anatomy and use of the OpT port to the Raspberry Pi. Guess we'll just jump right in. The intent is we may gloss over some of the slides. There are several sections with image captures that show or attempt to describe specifically what needs to be done. So follow up, we're more than happy to answer questions on that side. And we'll also make a virtual machine image available online in advance of the hackathon itself. Several people have asked what our motivation is for doing the port itself. We looked at it from the standpoint of the next generation devices need foundational security. And in terms of embedded systems that are based on ARM processors, whether they be Cortex V7, V7As, V8As, and the upcoming the trust zone for V8M, this is very rapidly becoming a means of enabling a broad variety of secure systems, peripherals, and management capabilities on chip. So the major appeal is a significant cost reduction for the device OEMs. One of the challenges that we have is there's unfortunately a lack of knowledge surrounding the trust zone and trusted execution environments. And one of the things we hope to achieve by making this available on the Raspberry Pi 3 is basically expand the base of people that understand the technology quite dramatically. One of the things we want to do is make sure that it can, that the use of the software can go well beyond people that understand hardware, spend their lives in data sheets and write software. So make it available to a much larger audience, and make it so that you don't have to be an OS or hardware guru in order to build an application. So for us, it's really about how do we make security accessible. The Raspberry Pi 3s are extremely affordable at $35. There's very good support for the hardware within the board support packages, so call it the 32-bit Raspbian environment and the online fora at Raspberry Pi. The SoC itself is fairly advanced, so it has a quad-core Cortex A53 V8 ARM processor on it. So we initially assessed sort of what would be involved in possibly doing a port to the device. And this is done without a data sheet. So we poked around the startup code, and it looked like some of the trust zone features might be present. High on our list is the ability to debug anything, so bringing a new chip or a new board up. So search for JTAG capabilities, found multiplexer setups for the pins that are on the header on the board, and sort of determined that a port of Opti might be feasible. For sort of jumping to the very end of this, for the memory map, so people who want to put this in the back of their mind and get early access, they can go to Linaro right now and build. This is the memory map for the device, and going to make the point right now that for aspiring malware authors, they need to only map a small chunk of physical memory, and they can stomp all over effectively what should be otherwise secure operating system. So the point we're making here is that the Raspberry Pi 3 architecture is not secure. It does not support secure boot. There are no means to segregate secure memory from non-secure memory, and there are no means to basically secure peripherals. So we view it entirely as being a development or educational platform, but it is not a security target. And as a result of that, JTAG works extremely well. There's no control that will get in your way that will prevent debugging, even trapping through all of the exception levels of the Cortex A53 cores on the device. For people who want to build their own connector cables, we basically provide the pinout on this page with the signals. And those that are in red correspond to the pin numbers for a typical 2x10 header on the bus blaster.
Sorry, there's a problem. The slides don't appear to be transitioning for some reason. So this is still stuck. I don't understand why. It was working earlier. I don't know why this is not moving.
Oh, so now?
Now they can see us clicking through.
Okay, good.
Okay, so just use this view, I think.
Okay, okay, that's fine.
Yeah,
that's fine. We'll just use that. So full screen mode, the app doesn't work.
Yeah.
All right, we'll just page down. Okay, so we'll walk through what's involved. Was this actually the slide we were on? Oh, we're actually quite a bit further down.
We're further down. So.
We're quite a ways down. We're down here. Okay, so it's describing essentially for people that want to wire their own cables. The other aspect of this is we use the mini UART on the Raspberry Pi 3 header as a serial interface. So wiring is attached. The configuration for OpenOCD for the A53 debug access port, they follow ARM v7a compatibility layout. Provided as well are GDB init files that load all of the symbols for all of the binaries that are 64-bit enabled. So AART64, so for U-boot, BL31, OpT, VM Linux, and the TAs. As well, we provided a port of AART64 into OpenOCD. as well as the configuration file for the Raspberry Pi 3. This only allows debugging of the 64-bit instruction set. If the core is in 32-bit mode, OpenOCD does not work. So we suggest that basically develop 64-bit TAs, and this way they can be debugged at source level. So what it allows is debugging anything of BL31 from the ARM trusted firmware, U-boot itself, OP-TEE, and the TAs, as well as Linux, because we're running a 64-bit Linux. The Linux itself is configured with a compatibility flag, so it's able to run, basically runs the Linux operating system in 64-bit mode, but the normal world runtime can be any mix of 64-bit or 32-bit. So I'll walk through the hackathon setup, the components of the kit, and the installation. So we're basically providing a number of components, and we'll want to walk through the various pieces. Unfortunately, there are a few moving parts. We figured the easiest way to address the entire setup is through a VirtualBox virtual machine. So included within the kit itself are Raspberry Pi 3, a Bus Blaster version 3 debug dongle with a mini USB cable that can be attached to the host. We provide a custom cable that allows for JTAG debug and USB serial console to the Raspberry Pi 3, a 16 gigabyte micro SD card with the entire setup already preloaded on it, a VirtualBox Linux machine exported in OVA format, which will be imported by the participants in the hackathon to their host environments. An example trusted application, normal world component, and also within the stack is the full operational source for the Linaro X-Test test suite. So this is 20-some thousand odd test cases that exercise the GlobalPlatform device. We've already, I think, described this. So effectively, the kit has pre-built into it the scripts for launching OpenOCD, and for performing the debug operations. We'll walk through that in a little bit more detail shortly. The prerequisites, so think in terms of pretty much any machine, any desktop these days. So Windows, Mac, or Linux host machine with VirtualBox installed, and I would suggest installing the VirtualBox extension pack as well. We are providing a micro USB cable to power the RPi 3, so those will be in the kits. You'll need the ability to read the virtual machine image from a micro SD card for the VirtualBox host environment. So, for example, whatever plug-in stick, or if the laptop or machine has a slot, then just plug it in directly. It's in a fat partition. Approximately 12 gigabytes of free space on the host are required for the expanded virtual machine, and you need 3 USB ports. So one for the Raspberry Pi 3 power, one for the Bus Blaster, and one for the serial console. Should note as well that the HDMI is enabled on the Raspberry Pi 3 and can be used as a console. So if you have some HDMI capability for a monitor and a USB mouse and keyboard, that the entire Raspbian desktop environment will come up on the HDMI screen and can be used. Caveat in terms of OpenOCD, it can debug Arch64 only. So it's able to debug several of the critical components. ARM firmware, BL31, OP-TEE itself, Linux, and 64-bit TAs. Interrupts are enabled during TA execution, so this complicates single stepping. So we recommend that people become familiar with setting, enabling, disabling breakpoints, and do this during successive runs. The RPi configuration itself has entries for all 4 cores on the chip. However, 3 of them are disabled. So to do that, you would uncomment the entries in the configuration file. U-boot itself is configured so that a variable called SMP controls single or quad core boot. And because of the Linux can arbitrarily schedule across 4 cores, we recommend that the debugging at the hardware level be done with SMP off. This is the default. I'll walk through VM installation. So first step is insert the micro SD card into the host and import the virtual machine image from the VM subdirectory of the boot partition. Under Windows, there is a naming problem, so you'll need to rename the machine instance. So it's just highlighted in the image capture. The second aspect, which is I would call a misfeature in VirtualBox, is that USB needs to be disabled before the at the point where the device has been imported before you attempt to boot it for the first time. It's a simple matter to open up the settings for the VM, go to the USB control, and just unhighlight the tick box in each of the selections. They will automatically be re-enabled by VirtualBox when you go to launch the machine for the first time. For people that aren't familiar with VirtualBox, they need to basically learn how to capture USB devices. There's another, let's call it a bug in the Linux implementation. Due to the security permissions in Linux, the desktop or invoking user must be a member of the VBox users group. I can verify that you're probably not part of this with the groups command under Linux. If you're not present on the host, then the command user mod is used to add. And in order for that to take effect, either log out and log back in or reboot the host machine. The VM itself is based on Ubuntu 14.04 Mint 17 mate distribution. We chose this because the Mint distribution is actually much simpler to configure in terms of already having what we call a very rich development environment in place, rather than sorting through dozens of missing dependencies in a stock Ubuntu build. Included within the file system are the full source for the Raspberry Pi 3 build, the scripts and the make files. The entire debug environment is enclosed, so OpenOCD, the configuration, startup script, example TAs. To the VM, you'll be logged in automatically at boot. Username is optee, and the password is optee. You can sudo bash, sudo bash to gain root access. The screen will time out with a screensaver, so just remember the password optee, all lowercase, no hyphens. The cabling setup is very straightforward. We've tried to make this easy and obvious. So at the bus blaster, it's a 10 by 2.1 dot pitch connector. The red wire goes at pin 1. For people that aren't familiar with using basically the terminology, if they're familiar with the Raspberry Pi, pin 1's typically at the upper left corner. We've indicated in the images, and on the bus blaster, it's labeled vtarget VTG. On the Raspberry Pi 3, similarly, pin 1 is in the same place at the upper left corner of the connector. It's an 11 by 2 on the cable. There are 9 wires that go to the bus blaster and 3 that go to a USB dongle, which is the console interface. On each connector, pin 1 is the red wire. It's right beside the label J8 on the Raspberry Pi. So again, just for those that want to build their own cable, just another instance of the slide so that it's quite readily available. I'm going to walk through how we basically bring up the board itself. Minicom is pre-installed within the VM. So if you want to capture the USB serial interface, you can do this. Would probably, if you plug that in first, it would probably appear as something like TTY USB 0. The console settings are 115.200, 891, or equally if you're running something like PuTTY, then similar settings, and just can do this naturally in the host environment as well. Since it's easiest to debug a single core, SMP should be off. So the screen capture shows what the situation should be. The board is set to not auto boot. The next step is to capture the device for debugging. So what will show up is actually a dual port FTDI interface for the bus blaster. Output of LSUSB will verify, as shown what's highlighted in the image, what should appear on your machine. To launch OpenOCD, we've created a shell script that has effectively the configuration baked in. So if you type OCD at a shell prompt in the VM, you should see something similar to what's highlighted in red, essentially saying that it's captured or discovered the single core and reporting 6 breakpoints and 4 watch points. To launch GDB, step into the Raspberry Pi 3 debug folder. There's a soft link made to the cross-target GDB instance, so make sure /GDB. This preloads all of the symbols for U-boot, BL31, optee, VM Linux, so the actual Linux kernel running on the device, as well as the Hello World TA. It sets an initial breakpoint within the TA disables that and leaves you staring at GDB not having resumed the core. At the bottom of the screen capture on the right, you'll notice that the Raspberry Pi 3 is now halted at EL3, so effectively in monitor mode, and you need to resume in order to boot. So type either continue or a C and press enter to bring the board back to life. You then return to the U-boot console and just type boot. You should see something start as is on the right image capture. So the kernel will load. It will transfer to ARM trusted firmware, start OptTEE, and hand off to Linux. Console login. So if you're attached to an HDMI monitor, you will eventually see the standard Raspbian desktop come up. But for purposes of what we're showing, use the serial interface, log in with the username Pi and the password Raspberry. So for those familiar with the Raspberry Pi 3, this is their stock setup. Become root, so sudo bash, and then launch the Hello World application, /hello world. So this will invoke the trusted application for as well, so within the secure world through OptTEE. The breakpoint has been disabled, so at this point, make a second run. Go into the GDB window, press Control-C, which will halt the CPU. Type ENA or enable *1, so the first breakpoint, and then continue. The core will resume, and then rerun Hello World from Linux. What you'll see is something that's depicted in the image on the right, where the CPU will halt. You'll be staring at a line of code where you can, for example, examine the contents of the parameter buffer that was passed into the trusted application. This is basically just an overview or summary of the above steps. So for those that are really adventurous, this is a layout of where they are. Under the Hello World directory of the Raspberry Pi 3 folder, you'll find subdirectories and a script. So as a starting point, we've done this to just run the script build hello world.sh. The TA output appears in the TA subdirectory with the extension .ta. The host output is in host hello world binary. Something to note is the trusted application itself is 64-bit. The normal world component is 32 bits. For those that are adventurous, if they want to understand or walk through or need working examples of the GlobalPlatform APIs, the Xtest test suite is included. So if you want to do anything with cryptographic or file system operations, this will give you very good source examples to start with. To install a trusted application, there's no security measures in place. There's no binding. There's no crypto. You simply drop the TA file into /lib/optee_armtz on the Raspberry Pi, and you place Hello World in a convenient place. So for example, Hello World can go in Pi's home directory. A few tips to avoid reboots of the board. Within an active GDB session, you can basically break. So with Control-C, type mon resume and then quit. And what this allows you to do is quit GDB, then you can restart GDB again. And if you've since done, for example, over the network between an update to the TA and the normal world component, you can restart a debugging session without having to reboot the board. So I guess a suggestion here would be for people to bring an RJ45 cable to connect directly between the Raspberry Pi and their host machine. They would just be able to FTP or SCP files directly across between the environments. For GDB itself, if you go through the init script, all ELF files are referenced within GDB init. So this gives essentially an overview of the address spaces as well, where all of the binaries are loaded. If you're going to change the UUID for the trusted application, then the name of the ELF file corresponding to the TA must be changed as well within the GDB init file. The load address for a single TA remains the same as what it is currently in the GDB init script. For debugging the normal world component, just use the GDB that's already on the Raspberry Pi 3 and we'll need to move the source across. But it's very much it's just a stock environment that you would find in a Linux system. It is the stock environment from the Raspberry Pi. Again, just an overview of the memory map. So for people who want to understand the layout, it's not complicated, and it took some poking around to discover where components could be put, because there effectively is no data sheet for the Raspberry Pi 3. We added also a ability to recover. So something we're going to strongly recommend: do not pull the micro SD card from the Raspberry Pi 3 with the power supplied, because it's highly likely that you will corrupt the FAT partition. If you do this, the board becomes unbootable. So what we did was we placed an entire copy of the FAT partition in the ext4 partition on the micro SD card under /boot. So typically when this is if you were able to mount this in your VM, then it will appear under media opti rootfs boot. All of the files in this directory can be recopied back to a newly cleaned FAT partition on the micro SD card, and you'll re-enable, basically bring the board back to life without having to figure everything out all over again. In the worst case, we'd suggest reformatting the FAT partition on the micro SD files and copy those across. If your VM is already up and running, there's no need to, I would say, capture or copy the virtual machine instance image, because it's about 40 gigabytes and will just consume time. We placed it there for convenience in case things go wrong. And I think that covers basically the overview that we wanted to provide today.
Thank you, Phil. There's a lot of information in here, obviously, and while the webinar itself is being recorded, we will be uploading these slides in the Insights section of the Be My App website, so you can refer to it over there. We can end early, and we can give you guys back some time. So once again, I want to thank everyone who's participated in the webinar today. This presentation, as well as a couple more, will be available on the Insights section of this website, of the Be My App website. And those should be placed probably in the next 24 hours or so, if not earlier. Additionally, on the Friday before the hackathon, we will go over some additional elements that will help get all the developers participating ready. We'll walk through an example of building a trusted application, so that you can you have a chance to see how the APIs are defined and what's involved. So one last thing I want to add is that Phil Atfield is going to be one of the mentors at the hackathon, as will Mike Hendrick, who's our VP of Product Development. So we look forward to seeing you at the hackathon in a couple of weeks.